Hey guys, welcome to Trade Science, and in this video we're going to be talking about walk-forward optimization. So walk-forward optimization is a technique in trading that's used to find the optimal parameters for a strategy. Now we've all pretty much seen backtests that might look like this, where we have, a really nice section of the equity curve, and this is what you're presented, and whoever's giving you the strategy is saying, I've optimized the parameters over this window, but what we really don't see is what it looks like going forward. And so this is a decent backtest, but I've chosen these parameters for this backtest to be the optimal. And so what we really want to do is see how this strategy is going to perform out of sample for the entirety of the backtest, so that every single trade that we're looking at is an out of sample result. And so the way we do that is we take our data and we're going to split it into sections. And so these sections are the in sample, shown in blue. These are where we're going to do optimizations, and the out of sample in orange. The out of sample is where actual trades that go into the backtests are going to be located. So you can imagine if we just collected all of these orange parts into one time frame, we would get a full time period of trades that were based on optimizations, but they're completely out of sample, meaning the optimization has not seen this data yet. And so let's go ahead and fire up VS Code. And we're going to be doing this walk-forward optimization in Vectorbt. Vectorbt is a lightning-fast backtesting framework built in Python. And you can see here that I am on the Pro version. So you may be able to follow along with this if you're not on the Pro version, but I highly recommend Pro. It's $25 and it's definitely worth it. Extremely fast and easy to use in my opinion. So we've got some imports here, pretty standard stuff. The only thing interesting here is I'm going to be setting some Vectorbt settings, but that stuff isn't super important. So the next thing we want to do is get some data. This is a function that I've actually written, but you can get your data however you want. Basically what this is going to do is it's going to load up all 28 major Forex pairs. So let's go ahead and have a look at this data so we can get the close price here. Maybe we want to look at the euro dollar and we want to plot that. So if we look at that, so we've got data from 2004 to 2015. Okay, so the next thing we want to do is develop a simple strategy. And for this video, we're going to use a simple moving average crossover strategy. I know, very boring, but it illustrates our purpose pretty simply. So for our strategy, what we're going to need is we're going to need the closing prices, we're going to need the slow period, and the fast period. So first thing we want to do is we want to fix our data up, and that means if we have any kind of non-number value in here, what we'll do is go ahead and clean that up. Vectorbt has a built-in function for that. The next thing we want to do is actually import the TALib library. This is going to allow us to calculate our moving averages. So with that imported, we can go ahead and calculate our moving averages. Now that we have our moving averages, let's go ahead and check that function out, make sure it's working so far. So we'll do SMA cross. Oh, and we actually want to return something here. Okay, so that appears to be working. So the next thing we want to do is we want to create some strategy entry and exit signals. And again, Vectorbt has some really simple functions for us. So what we've done here is we've gone ahead and used some helper functions inside Vectorbt, and this is going to detect if the fast moving average crosses above the slow moving average, and similarly for the short entry using crossed below. So this should return an entry Boolean array based on our close prices. And so this appears to be working well. I'm happy with this, so we're going to return long entry and short entry here. And then what we're going to do is we're going to go ahead and wrap this into a helper function. And so what I've done here is I've got the indicator factory for Vectorbt, and this is just going to allow me to use some built-in Vectorbt methods on this function so that we can create parameter combinations and stuff like that. So what we've got here is that we're saying that it takes the closing prices, it takes parameters, slow period, fast period, and it outputs, we're not going to put trend out on this one, but it outputs long entries and short entries. We named it SMA cross, and so we're using this apply func method here of the indicator factory. And we're also saying that it takes 1D, and then we're setting some defaults here. So go ahead and test this out. So we're going to call our thing strategy, and we'll do strat.run, and then we're going to pass it data.the closing prices and nothing else. Let's just see what happens with that. So if we do strategy.long entry now we can see that for every single symbol that we have in our data set, we've got the entries for long positions. You see these are all false, but somewhere in there there's going to be some trues so that we can enter positions. Perhaps the next thing we want to do is calculate our strategy's performance across a bunch of different parameter combinations. So what we're going to do is go ahead and copy this, and in here we're going to put some arrays for slow period and fast period. For slow period, maybe we'll do 40 to, 150, and we'll do that by 5. Dtype here is going to be integer. And for fast period, we'll do that. So the last thing, the most important thing here is we're going to put in param product is equal to true. Now if we do this, we're basically going to calculate the product of those two parameters. So what that means is if we look at these long entries now, you can see that we've got two new column indices, and those correspond to the strategy slow period and strategy fast period. And so this is a huge data frame now. You can see we've got 3,000 columns and 3,200 rows, so it's absolutely massive. And now what we want to do is we want to run a strategy. One thing I'll do first is I'm going to use one of my built-in functions that I created to get some position sizes for this. So all I've done here is I'm using a 4x position sizing function that I wrote that accounts for some different things, cache level and the amount of risk, in this case 2%. So we've got our position sizes. Next thing we want to do is go ahead and run this. And so we'll do Vectorbt portfolio from signals, and we've got data. For entries, we're going to do strategy.long entry. For size, we're going to put in my position sizes, and then something here, size type is equal to amount. I'm going to go run this, and now the first time I run this, it's going to take a couple minutes. Oh, we got allocation probably too large. Basically, I'm going to go ahead and change a couple things here. So I'm going to run this. You can see how quick that runs, right? So this is extremely fast. I'm actually going to turn this back down. Okay, so we were able to run an even larger one. The next thing I'm going to do is I'm going to collect the performance here. So I'm just going to copy this in. This is something I have in another notebook. So what we're going to run is the stats method on this portfolio. We're going to get the total return, trades, win rate, and expectancy, and we're not going to aggregate that. So if we grab that, this is what it looks like. So you can see we have our parameters over here on the left, our symbols, and we've got total trades, win rate, all that good stuff. Now you might be thinking, well, let's look at the best set of parameters per pair. And so the way we would do that is we would use group by, because this is a pandas object. We want to group by symbol, and let's say we want to look at top expectancy per pair. So here you can see that we've got the best parameters for each pair. We can plot this using the built-in Vectorbt plotting method. And here we want to set the column parameter for the plotting method. And so we want to look at something here. So let's go ahead and look at the euro pound. And so we can go ahead and do fig.show. You can see here this backtest is not super impressive, but this is just a demonstration. So it's obviously simple moving average crossover. It's nothing super technical. But you might be thinking, how do we go ahead and run this optimization over and over a period of time and split it into in sample and out of sample? We can actually do this in Vectorbt quite easily. So we're going to do that by first creating a splitter. So in Vectorbt, the way walk forward and general cross-validation is performed is using a splitter, and a splitter will produce this chart that I showed you in the beginning. And so this is basically a data structure that has in-sample and out-of-sample date ranges, and it has methods that make accessing them very easy. So one of the first things I want to do is I want my splitters to use one of my custom functions. So I'm going to go ahead and paste that in here. That custom function basically takes the length of your data. It takes a train test split fraction. So this is a percentage of each set that you want to be your training data. So in this case, each set is going to have 75% training data. And then I want 10 sets. So if I run this function, this is for my index. It's going to print the length of the in-sample period and the out-of-sample period. So you can see here that we've got almost 75% training data, and we're going to use this as input to the split function, and we're going to use the split function inside of the Vectorbt splitter. So I'm going to paste in the split function that I use. Feel free to pause on this. All you really need to know here is that it takes the in-sample period length and the out-of-sample period length, and it returns a split. And so we're going to use that inside the splitter class. And here we're using the from split func method. It takes the data's index, takes the split func, and it takes some other arguments here. So these are arguments that can pass to the function, so split, bounds, and index. And then we've got some keyword arguments here that are getting passed in, and those keyword arguments are equal to these in-sample and out-of-sample lengths that I found here earlier. So if I run this, split here, if I run this, we get our splitter, and that has a nice built-in plot method. And that will show us that graph that we did earlier. So the nice thing about this optimized split method that I wrote is that I can change this to, let's say I want 5 sets of splits. So now I've got 5 sets, 1, 2, 3, 4, 5. And so by passing it the number of split folds that you want, and then the train test split fraction, it's going to go ahead and calculate the in-sample and out-of-sample periods that get closest to this fraction. It's not perfect, but it's very close. So the next thing we want to do is calculate strategy performance. So the way we calculate strategy performance is by first creating a function that takes in our data, our strategy, and it outputs some metric like total return, Sharpe ratio, something like that. So the way we're going to do that is first we're going to use a parameterized wrapper from Vectorbt. And then what we're going to do is define the performance function. For our metric, we're going to use the total return, but you can set this to whatever return you want to use. And now we're just going to run our portfolio inside this function. So we're going to go back up here, and we're going to go ahead and copy this portfolio call into here. I'm going to clean this up a little bit. So the only difference here is I'm going to call our strategy int here for short for indicator. This is just normally what I do. And then what I'm going to do is we're going to say result equals pf dot get attribute, and from attribute we're going to get metric. So this is the same as saying pf dot total return, right? But we're allowing the ability to pass in whatever metric we want here. And then we're going to return that result. The next thing we want to do is use the splitter's built-in apply method to calculate the results over our training data. So we'll do train performance. On the apply method, it's going to take our performance function, and then it's going to take all of the arguments of our performance function, but we're going to use the splitter module of Vectorbt to take our in-sample data. So we're going to do vbt.takeable data. I'm going to go ahead and copy this, and then it's going to take our strategy. Again, we're calling that indicator here, but above we called it strategy. So that's all of our entries and exits over all the different parameter combinations. And it's going to take our position size. We're going to leave metric at total return. We are going to set some settings here. I'm going to copy these in from another notebook. So we're going to show our progress. We're going to do some memory management stuff here. We're going to pass in our set. So our set here is in sample. So if we pass out of sample here, it's going to take the out of sample splits from our data, our strategy, and our position size. So this is what makes Vectorbt very cool. So if we go like this is going to run our training performance. And if we look at that, okay, something's wrong here. We have to return the result. If we look at that, now we'll have our split number. So you'll see we have we have 5 splits. We've got our strategy slow period, fast period, and then we've got the return over here because we've asked it to output the return. So you might be thinking, how do we take this information and then run a full walk forward optimization based on this? So the way that we're going to do that is we're going to do some simple indexing type stuff. So the first thing we're going to do is look at our best parameters per split per symbol. So we can do that using the pandas group by method. And we want the max index. So if we look at best now, so for each split and for each symbol, we're going to have our best parameters. You'll notice here that we also have the split number here. We also have the symbol, which we may not be interested in. So let's go ahead and get rid of the split number. So the way we do that is pretty simple. We want to pass back a tuple. So in this case, we only want index 1, 2, and 3. So we'll use some list comprehension for that. 1, 2, 3, for I in best. Look at best now. We got rid of the split number off of that. And we can use this to index our strategy and get only the columns that we want from it. The way we're going to do that is by looping through all of these parameters and splits and assembling a data frame of optimized entries and exits. So let's do for I in the in best.index, and we want to get the level values here for split and unique. So if we print I here, basically we got split 0, 1, 2, 3, 4. So 5 splits. So for each of those splits, we want to get the out of sample entries. So we're going to take the out of sample entries for each split, and we're going to concatenate all of them into a single entries data frame that will feed to our strategy. What we'll do, we'll name some dummy variables here. So optimize long entries. And we'll do splitter. So this is our splitter class. And what we'll do is we'll tell it, I want the out of sample data, and we're going to take long entries. And so if we look at this, we've got our split, our slow period, and basically this is going to be a data frame. So what we want to do is we want to get the correct split. So if we go by here, index by I, now we get a data frame out, but this data frame has all of the columns in it, but we're only interested in the best parameters from the training data. So we need to index this again by the best and the corresponding split. And now we'll get that. So now we have the best parameters for the out of sample data across all of our symbols. So you'll notice that the parameters are a little different for each one of these. So what we want to do is go ahead and drop some levels off of that because we don't need to see the slow and fast period anymore. So what we're going to do is drop level, slow period, and across axis 1, drop level. So now we only have symbol, and this is good. So we're going to go ahead and replicate this to get the short entries. So that should be the short entries as well. Okay, that's working. And we want to just create some lists that we will add these results to inside the loop. So now we can run that loop and we'll get a list, and we can create that, we can concatenate that list of data frames into a single data frame. So now if we looked at our optimized long entries, what are we looking at here? We're looking at 2,500 rows, and this is starting on June 5th. You might be wondering, well, why doesn't it start in 2004 with the rest of the data? Well, it starts when the first out of sample period starts. As fate would have it, it's June 5th. What this has done is we've taken the best parameters for each training set, and we've taken all of the long and short entries corresponding to that best parameter combination, and we've assembled them into an entries and exits, entries, we're not doing exits here. So we can grab that portfolio method out of our training performance function here, throw it down here. So if we want to run our walk forward optimization, we're going to run it over our full data. But this time, we want to use our optimized entries for long and short. That's that. So if we want to look at the results of this, I'm just going to go ahead and copy this from up here. Let's say we want to look at our plot. Now remember, we don't have parameters on this data frame. So if I want to compare the euro pound to like we did above, I'll plot like this. You can see this result is quite bad. So in the plot above, we picked the best results. So this is the difference between picking the best results and from doing what you would actually do in real life, which is optimizing and then trading. And now this doesn't say that optimizing is bad or walk forward optimization is bad because it doesn't work for this strategy. This is basically saying that simple moving average crossover strategy doesn't have a whole lot of information content in it by itself. One cool thing that we can do here is we can tell it to run over all of our pairs so that we have one shared account that trades all of the pairs simultaneously and see what that looks like. So the way we do that is by passing the group by to our portfolio, and here we want to pass it a list that tells it which group each column is in. So each column up here is a symbol, and we're going to pass in our length times the data columns. Okay, so this is a list of zeros. We could have used numpy.zeros if we wanted to, but this works. This is saying that all of our pairs are in group 0. We run this, that runs. This time we're having a shared account, so we don't need to specify column. And you can see our results here. And so you can see in the background is the benchmark return. So this is a combined return of all of our Forex pairs. You can see we actually did quite well here in the beginning, up to 10% quite quickly. But overall, this doesn't work very well. So you might be thinking, well, that's a lot of work to do walk forward optimization. But you can simply put all of this into a function and do a walk forward optimization very quickly. So that's how you go ahead and perform a walk forward optimization in Vectorbt, and more generally how walk forward optimizations are performed. Now I know I didn't go super in depth in this video, but if you leave a like and subscribe, I'm going to be covering some of these topics in greater detail in future videos, as well as indicator reviews and some other cool stuff.